At almost midnight on April 24th at Cape Canaveral's Launch Complex 34, the scheduled 10-hour-long countdown began for the launching of the second Saturn flight test vehicle, SA-2.
Sequence quarter slow. 8 PSI.
All automatic propellant loading and sequencing processes were conducted satisfactorily. The countdown proceeded without a single technical hold.
Telemeter recording on.
One 30-minute range hold was called, however, until a ship could clear the range area.
20 PSI on the LOX tank. 22.
Shortly after 9 a.m. on April 25th, 6 months after the spectacularly successful first Saturn flight, the countdown for SA-2 had reached its final seconds.
All nice protected.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Ignition, thrust buildup, and liftoff were normal. Objectives of the SA-2 launch included flight testing of the booster stage and operational testing of associated launch facilities. Structural integrity of the Block 1 airframe and aerodynamic characteristics were confirmed, and capabilities of the control system demonstrated. The propulsion system performed normally throughout powered flight. All electrical networks and instrumentation functioned properly, with very satisfactory telemetry signals received. Maximum velocity of over 3,700 miles per hour was attained. The sloshing effects observed during the SA-1 flight was reduced to an acceptable level. Cutoff occurred at 110 seconds for inboard engines and 116 seconds for outboard, as predicted. In virtually every respect, the SA-2 flight was successful. SA-2 also carried out a secondary or bonus scientific experiment known as Project Highwater. At an altitude of 65 miles, the vehicle, whose dummy upper stages carried 23,000 gallons of water as ballast, was purposely exploded to investigate the optical, ionospheric, and meteorological effects which water vapor has on the high atmosphere. About 15% of the water evaporated, and the remaining 85 tons formed a cloud of very small ice particles along the remainder of the vehicle trajectory. Prior to SA-2's flight, laboratory experiments in connection with Project Highwater were conducted at Marshall Center's Astronautics Division. Saturn flight conditions are simulated by using a vacuum chamber. To facilitate viewing, coloring is added to the water in the test tube. In this experiment, the tube is suspended in the horizontal position. A solenoid-operated hammer breaks the tip, releasing the water. Because of the low pressure, the water evaporates rapidly. Cooling is so fast that ice flakes form immediately. With the tube in this position, water boil-off is slow and sporadic. In a second experiment, a vial is suspended vertically. The tip is broken and a boiling reaction occurs. With the vial vertical, water boil-off is constant. In both experiments, pressure is so low that the ice which is formed has an unusually low temperature. Ice maintained at this temperature is very hard and elastic. Static test firings of the third Saturn flight vehicle, SA-3, were held at Marshall this quarter. 2 of 30 seconds duration, and the final one running 119 seconds. Defective bearings and main shafts resulted in excessive turbopump vibration in the first test. Defective parts were replaced, and pumps and engines were satisfactorily retested before the engines were reinstalled. Later firings encountered no difficulty. Assembly of the booster for the fourth Saturn flight test vehicle, SA-4, was completed on May 28th, and the stage is now undergoing pre-static test checkout. Fabrication of components and subassemblies, such as this thrust frame barrel assembly, for the fifth Saturn flight booster, SA-5, first of the Block 2 series, was carried out this quarter by Marshall's Manufacturing Engineering Division. A number of new fabrication fixtures, such as this one for making Saturn spider beam assemblies, have been placed into service for Block 2 booster fabrication. Looking toward future fabrication techniques for Saturn or other space vehicles, Marshall engineers are investigating exploding bridge wires in a fluid media as a means of forming and working metals. In this test, a piece of flat stock aluminum is loaded onto a female die and securely mounted. A crane hoists the die and stock into the forming tank, which is filled with water, and the exploding bridge wire is properly positioned. The ultra-fast discharge of a large capacitor bank explodes the bridge wire, creating a high-energy shock wave in the water. This shock wave, along with hydrodynamic pressure pulses, forms the metal into the previously evacuated die. Advantages of forming materials by this method lie in the control of forming and relative ease of operation. Hayes International Incorporated in Birmingham is fabricating several Block 2 booster components, including fins, lower shrouds, and engine skirts. Fin design utilizes the spar, rib, and skin type structure, which provides a high degree of structural reliability. 3 basic fin configurations are used. 4 large fins will be located at 90-degree intervals around the booster. 2 configurations of stub fins will be located at right angles to each other between the large fins. 3 of these have provisions for venting liquid hydrogen from the vehicle's second stage. In addition to providing flight stability, these 8 fins have vehicle support and hold-down fittings. The lower shroud, which Hayes makes for Saturn Block 2 boosters, is basically a corrugated skin structure with continuous rings supporting the entire unit. Republic Aviation Corporation of Long Island, New York, is another prime example of industry at work for Saturn. One of the world's largest banks of numerical control machines, which operate from taped manufacturing instructions, is being put to use by Republic Aviation for fabrication of a large number of various Saturn components. The first of the Saturn LOX and fuel tanks, manufactured by Ling Temco Vought near Dallas, Texas, were delivered to the Marshall Center this quarter. During transportation, the tanks are protected from damage by a custom-made shipping container. Marshall personnel thoroughly inspect each tank prior to acceptance. Tanks are subjected to an air pressure leak test, with Freon used as a tracer gas. If leakage exists, an electronic instrument detects the area of escaping gas. Delivery of the H1 engines, both inboard and outboard, for the SA-5 booster was accomplished early in April by the contractor, Rocketdyne Division of North American Aviation Company. Small model rocket engines, such as this 500-pound thrust H1 model, are being fabricated by the Marshall Center's Test Division for use in gathering data about their real counterparts. 1/10 scale models of the C-1 Saturn's booster and S-4 stage have been tested in a high-altitude chamber to study interstage separation problems. Test objectives were to obtain data on pressure versus interstage separation distances and to determine the effect of a modified conical flow deflector on the hot gas backlash. A 1/20th scale model of a Block II Saturn booster was tested in conjunction with a model flame deflector of the type intended for use on the launch pedestal of Launch Complex 37, now under construction at Cape Canaveral. This test program enables engineers to study base region environmental pressures, temperatures, and heating rates, as well as flame deflector effectiveness under hot firing conditions. The new Block II Saturn booster assembly station was installed during this report period in Marshall's recently expanded Saturn Assembly Building, which now contains over 200,000 square feet of floor space. The tooling ring for the SA-5 booster has been fabricated, and work is scheduled to begin in July on SA-5 booster assembly. Selection of International Business Machines Incorporated, Owego, New York, to develop the guidance computer for Saturn C-1 was announced this quarter. For test purposes, the computer will be aboard the SA-5. Also slated for initial use on SA-5 is a new camera eject mechanism which will help to provide a photographic record of vehicle actions. Along the spider beam of the SA-5 booster, 8 movie camera pods and paraballoon recovery packages will be mounted into ejection cylinders. In this laboratory test at the Marshall Center, gaseous nitrogen is used as a pressurant. When sufficient pressure is attained, the firing switch is closed and the camera pod and recovery package are ejected. SAD, the test vehicle which had provided vital dynamic vibration data contributing to the success of the first 2 flight vehicles, was removed from Marshall's dynamic test stand this quarter, its mission completed. A new vehicle, SAD-5, a simulation of SA-5, will be built at Marshall and later installed in the stand for testing. Marshall's static test stand will soon be modified to accommodate 2 Saturn C-1 boosters simultaneously. The old test position in which Jupiter and Juno 2 rockets were once tested has already been removed in preparation for creating a second Saturn booster test position in its place. Several major construction projects are changing the Marshall Center horizon. The 9-story central laboratory and office building, scheduled for completion next January, will be the center's tallest building. Personnel of the Propulsion and Vehicle Engineering Division are due to begin occupying their new 5-story addition in July. And Manufacturing Engineering Division has already moved into its recently finished addition. At ME Division, A group of Chrysler engineers and technicians are presently receiving orientation on Saturn fabrication and assembly methods in preparation for Chrysler's future C-1 booster manufacturing at Marshall's Michoud operations plant near New Orleans. 20 miles from Michoud at Slidell, Louisiana, this new $2 million building has been acquired by NASA from the Federal Aviation Agency. The building, which contains 53,000 square feet of floor space, is being occupied by some 500 Chrysler employees in a move to alleviate a critical office space problem at Michoud. At the Mississippi Test Facility site, negotiations are now underway with some 200 landowners in the construction area. The government schedule calls for outright acquisition of title to the area by July 31st. Construction of Saturn Launch Complex 37 continued at Cape Canaveral during this report period. Work includes construction of the mobile 3,500-ton steel service structure, 268-foot-high umbilical tower and steel launch pedestal, circular concrete blockhouse, locks and fuel storage facilities, and servicing facilities. Construction of major items is about 60% complete and progressing on schedule. When finished, Complex 37 will have 2 Saturn launch positions, utilizing a single control center and service tower. At Douglas Aircraft Company, contractor for Saturn's S4 stage, cold flow tests have been successfully completed at the Sacramento test facility using a single RL-10 liquid hydrogen liquid oxygen engine. 5 additional engines were received this quarter from Pratt & Whitney. After acceptance checking at Santa Monica, the engines were shipped to Sacramento and installed in the battleship test vehicle in preparation for the second phase of the battleship test program. Modification of test stand number 2, which will be used for the all systems testing, continues on schedule. The steam system was being installed during this report period, and other necessary hardware is now available for completion of the stand. The Cornell Aeronautical Laboratory, Buffalo, New York, has been conducting a series of tests with an S4 model in an altitude chamber, looking toward solution of problems which occur when a portion of the engine's hot exhaust gas escapes from the exhaust plume and flows into the base region. During this test, which lasts for only 5/1000ths of a second, pressure and temperature measurements are taken on the base plate of the model using miniature, highly sensitive instruments. Piezo electric pressure transducers are mounted behind orifices in the base plate at locations where pressure is to be read. Fragile thermometers consist of a thin film of metallic paint applied to a quartz button. When the surface of the button is heated by the gas, the electrical resistance of the metallic film changes. Then, the output voltage signal of the thermometer denotes the instantaneous temperature of the particular location under survey. By observing the time history of this temperature, the local heating rate is determined. Fast-responding instruments such as these permit Cornell Aeronautical Laboratory scientists to study rocket base heating problems in short-duration experiments. Such tests are better controlled and much more economical to perform than conventional techniques involving continuous operations. Here is one frame taken from a high-speed Schlieren motion picture film showing shock waves created by the combusted gases exhausting into the vacuum chamber. Preliminary flight rating endurance testing of the S4 stage's RL-10A3 engine was successfully completed on June 9th by the engine contractor, Pratt & Whitney, at West Palm Beach, Florida. "26 PFRT firings totaling 4,096 seconds were conducted. initial inspection showed the engine to be in good condition. A series on non-firing gimbal tests of the RL-10A3 using Douglas Aircraft Company plumbing connections was also carried out. To test engines and hardware for possible structural weakness, a stress coat was applied on metal surfaces to locate areas of structural yield. Various gimbal angles and frequencies were applied to the engine to simulate the worst expected flight conditions. Both engine and vehicle plumbing withstood the tests satisfactorily. In support of the engine program, facilities completed at Pratt & Whitney's Research and Development Center this quarter included a new vertical single-engine test stand and a 90,000-gallon vacuum-jacketed liquid hydrogen spherical storage container. As progress continued this quarter on the Saturn C1, shown alongside the Statue of Liberty in an artist's conception to dramatize its great size, work was also underway on the even larger Advanced, or C5 version of Saturn. The C5 will stand about 350 feet tall, as compared to 170 for C1. The C5, shown in model form, will be able to hurl over 200,000 pounds into a 300-mile orbit. The vehicle could use 2 stages for Earth orbit missions and 3 stages for escape missions. Launching of the first C5 is expected in 1965. At Marshall, construction is proceeding on the static test facility to be used for testing C5 boosters. The concrete foundation for the massive stand plunges over 45 feet into the Earth. Including its crane, the new test structure will be 405 feet tall. Over 1,000 employees of the Boeing Company, contractor for the Saturn C5 booster, are now at work in the Huntsville area. The company is expected to employ more than 1,500 there during 1962, most of whom will later be transferred to Marshall's Michoud operations, where the giant boosters will be manufactured. At North American's Aviation Space and Information Systems Division, contractor for the Saturn C5's S2, or second stage, work this quarter included hot flow tests using scale model engines with a model flame deflector of comparable scale to determine optimum engine orientation for the 5-engine S2 configuration. Secondary objectives of the tests include determination of various deflector parameters such as pressure, temperature, and heat flux profiles, plus investigations of film coolant injection methods. The scale model engines produce a total thrust of 5,000 pounds. The deflector is coated with zinc chromate paint, which burns away during firings to reveal areas of probable burn-through. Fabrication of an S2 stage and transporter model designed to verify that the booster transporter will meet all maneuverability requirements is now complete. Using a road gauge fabricated to the same dimensions as the S2 transporter, a month-long survey has been conducted to determine the feasibility of routes proposed for overland transportation of the stage from Port Hueneme, California, to North American Static Test Facility at Santa Susana, a distance of some 50 miles. A plaster model has been made to serve as a tooling aid for constructing a female layup die, which will be used to form bulkhead gore segments for the S2 mock-up. The sweeping frame employed in this operation will later be used to sweep the production tooling master. Two antenna radiation pattern models of the C5 Saturn have been completed, and one has been shipped to the Los Angeles division, where initial testing will be performed until the S and ID antenna range is operational. The program will determine the numbers and types of antennas required for telemetry, command control, and tracking aids, and will establish specific locations and angular orientation of antenna types selected. A highly significant advance in the Saturn program occurred this quarter when the mammoth F1 engine, 5 of which will be clustered for the C5 booster, underwent its first full-duration static test at full thrust of 1.5 million pounds. The test was conducted at the NASA High Thrust Area at Edwards, California, by the F1's developer, Rocketdyne Division of North American Aviation. The ground test was sustained for 151.8 seconds, approximately flight duration, before being terminated as programmed. It was the longest test to date by the only single rocket engine known to have been operated above 1 million pounds of thrust.